Every time we lift an object at a certain height, we are actually storing some energy on it. Pulling the spring on a pinball game will give the spring needed energy for the ball to gain speed once hit by the spring. To lit up a flashlight, the stored energy from a battery is converted into electrical energy. These forms of stored energy are called potential energies. Potential energy is a form of energy stored on a body due to its position, state or shape. It may be in the form of gravitational, elastic, electrical, and magnetic in nature. In this unit, we are going to consider, for the meantime, only two forms, the gravitational potential energy, and the elastic potential energy. Now let us discuss gravitational potential energy. Imagine a ball of mass m, located at a certain height h, above some reference point, let's say the ground. The ball possesses stored energy called gravitational potential energy. Gravitational potential energy, denoted by U sub grav, is the energy which a body possesses because of its position or height relative to some point of reference. For an object located on the small region from the Earth's surface, gravitational potential energy is expressed as the product of mass, m, gravitational acceleration, g, and height h. The SI unit of gravitational force is joule, for as long as mass is in kilograms, g is 9.8 meter per second squared, and height from specific datum is in meter. From this equation, we see that the magnitude of potential energy of a body depends on its height relative to a chosen reference point. Imagine we have chosen 3 reference points or lines, from which the gravitational potential energy of a body is determined. Let's say the body is, again, a ball of mass m, which is located on reference point A. The gravitational potential energy of the ball depends its height relative to the 3 reference points A, B, and C. The potential energy of the ball relative to point A is 0, since the ball is already located at point A, and its height from point A is 0. Since the ball has a height h sub b, so the ball has potential energy relative to point B, and its magnitude is expressed as mg times h sub b. The ball is located at a height h sub c, so its potential energy relative to point C is mgh sub c. Take note that the potential energy of the ball relative to point C is greater than the potential energy of the ball relative to point B, since h sub c is greater than h sub b. We clearly see that the gravitational potential energy is a function of height. The higher the body is placed above the reference point, the higher the potential energy that can be stored on the body. Now, let us do some problem solving involving gravitational potential energy. Problem number 7. What is the potential energy for an 800 kg elevator, at the top of a building, 80 meters above street level with respect to, letter A, the ground, and letter B, the top of the building? Let us imagine that this is the building, from which a 800 kg elevator is located, 80 meters above the ground. So we are required to determine the potential energy of the elevator with respect to ground. And letter B, its potential energy relative to the top of the building. Again, this problem is not that challenging. For letter A, from the basic formula of gravitational potential energy, mgh, we have already mass, 800 kilograms, g is 9.8 meters per second squared. And what is our height? Since our reference point is the ground, the height of the elevator is 80 meters. So substituting the values from the equation, the potential energy of elevator relative to ground is 627,200 joules. Letter B, for the potential energy of the elevator, relative to the top of the building. Since the elevator is already at the top of the building, the height h is already equal to 0. Therefore, its potential energy is 0. Don't forget, the potential energy of a body relative to its current location is always 0. That's it. I'm pretty sure you're able to catch up with me. See you later. We learned from Unit 2, that a free-falling body experiences a net force equal to its own weight. The weight of the body causes it to accelerate as it moves downward, and to decelerate as it rises. With this motion of a free fall, we can say that the body's weight is doing some work on it. If you release a ball at an initial height h sub I, due to its weight, its elevation decreases to a final height h sub f. We see that it moves with a downward displacement delta y. Therefore, this net force or the weight of the ball, performs work. And the value of this work is a positive, since the force and weight are in the same direction. On the other hand, as the ball rises from an initial height of h sub I, it decelerates because of the downward force weight, while changing elevation to a final height of h sub f. As you can see, the displacement is upward. Therefore, the weight of the ball performs negative work, since the ball is moving against the gravity as it rises. With these two scenarios, we see that the work done by the weight, or the work done by the gravity, causes a change in potential energy of the ball since its height changes. And this work done by the gravity is equal to the negative change of the body's potential energy. Expanding this equation will give, negative of m, times g, multiplied by the change in height, h sub f minus h sub I. Take note that this formula is applicable whether the body is falling or rising. Do not remove the negative here. It applies to both falling or rising. Let us solve this problem. Problem number 8. A 0.3 kg ball is dropped from the top of a building, whose height is 100 meters. What is the work done by the gravity when, letter A, the ball is 30 meters above the ground? Letter B, when the ball hits the ground. So imagine this is the building, and this is the ball of mass 0.3 kg, dropped from this building, at an initial height, h sub I, of 100 meters. So for letter A, we are going to solve for the work done by the gravity, when the ball reaches a final height h sub f, of 30 meters. While for letter B, we will determine the work done by the gravity, when the ball hits the ground, that is, h sub f is 0. Now for letter A. We will use the formula, work done by the gravity, W, which is equal to the negative of the change in potential energy of the ball, or that is negative of mass m, times gravitational acceleration g, multiplied by the change in height, h sub f minus h sub I. Substituting the values, so we have negative 0.3, times 9.8, times the quantity 30 minus 100. So the work done by the gravity on the ball, from the top of the building to a 30-meter high, is 205.8 joules. For letter B, we will use the same formula. But this time our final height, h sub f is now 0. Again, substituting the values. The work done is 294 joules. As expected, our answer in letter B is greater than in letter A. This is because that, in letter B, the ball has larger value of displacement. 100 meter as compared to 70 meters from part A. This amount of work can be actually partly converted into thermal energy, once it hits the ground, that causes the temperature of both the ball and the ground to increase. This also happens when an explosive freefall bomb hits the ground. The work done by the gravity on the bomb is converted into thermal energy, enough to break apart the bomb that carries lethal and non-lethal substance, called payload. And this is the negative side of technology, the creation of weapon of mass destruction, instead of promoting peaceful life. And as future engineers, don't be an agent of devastation. We teach, you gonna learn, and use your learnings for your own benefit and for humanity as well. Potential energy is also involved in deformable materials such as springs and band. A stretched rubber band, a wounded-up torsion spring, a compressed spring, and a stretch bow rubber band have a form of stored energy called elastic potential energy. This form of energy can also produce work. In this section, we will focus our discussion on the property of an ideal. Before we take into consideration on the amount of stored elastic potential energy on the spring, let us first discuss how force affects the deformation of the spring. Imagine this spring is at equilibrium position. Equilibrium position means that the spring do not experience any amount of force. It is not stretched nor compressed. We have here the robotic arm that can apply axial force on the spring. As you can see, to stretch the spring from its free length, or equilibrium position, a force must be exerted. Increasing the force also increases its elongation. Increasing the pull axial force also makes the spring longer. Here we see that when applying a force F of 100 newtons, causes an elongation of 0.1 meter to the spring. This force is directly proportional to a distance x and is given by the equation, force F is equal to spring constant K, multiplied by distance from free length x. This also applies when the spring is compressed. As we increase the compressing force, the spring gets shorter. Now let us try to understand the meaning of spring constant K. Imagine we have two springs, spring E and spring B. As you can see, they have different diameters. It looks like spring A has a larger diameter than spring B. Spring A stretches by 0.1 meter by applying a force of 100 newtons, while spring B stretches by 0.2 meter, applying the same amount of force of 100 newtons. We see that spring B stretches more than spring A. Now if we compute the spring constant of these springs, using this formula, so spring constant K will be, force F, divided by the distance x. So the spring constant of spring A, 100 newtons divided by 0.1 meter, is 1000 newtons per meter. While the spring constant of spring B, 100 newtons divided by 0.2 meter, is 500 newtons per meter. We see that spring A has a larger value of spring constant. It means that spring A is more stiff or rigid than spring B. Therefore, we can say also that, the greater the value of spring constant K, the harder the spring to be stretched or compressed. Also, we see that the effect of the diameter of spring to the value of the spring constant. Large diameter springs have also large values of spring constant, hence more rigid than those springs with small diameters. Now, let us consider the amount of elastic potential energy stored in a lateral spring with a spring constant of K, when it is compressed or elongated at certain amount of distance x. When the spring is stretched or compressed by a distance or length x, the spring has an elastic potential energy whose magnitude is given by the equation, 1/2 of K multiplied by the square of the distance x. The SI unit of elastic potential energy is joule, for as long as the spring constant is in Newton per meter, and the distance is in meter. This formula also applies when the spring is compressed. As we elongate or compress the spring, the amount of force varies. And moving one end of the spring from its initial position x sub I, to a final position of x sub F, work W must be done on the spring by these varying forces. The magnitude of work is actually equal to the change in the elastic potential energy of the spring, or that is also 1/2 of spring constant K, multiplied by the quantity square of the final position x sub F, minus the square of the initial position x sub I. Now, if in case we stretched the spring from its equilibrium position, always set the value of the initial position, x sub I to 0. This is also the formula that we are going to use, when we are asked to solve the work done in compressing the spring. Now, let us do some problem solving about spring. Problem number 9. A spring requires 50 newtons of force for 5 cm elongation. Letter A, what is the spring constant? Letter B, how much work is done to stretch the spring at this length from its equilibrium position? So this is the spring at its equilibrium position. As this robotic arm exerts a force F, of 50 newtons, the spring is stretched by 5 centimeters. The problem requires us to determine the spring constant, K, and the work to be done in stretching the spring to 5 centimeters or 0.05 meter. For spring constant K, from the formula, force F, is equal to spring constant K, multiplied by the elongation x. Solving for the spring constant K, we divide both sides by x, so the spring constant is equal to force F, divided by the elongation x. Substituting given information, 50 newtons divided by 0.05 meter. So the spring constant is 1000 newtons per meter. Its value means that in order to stretch the spring by 1 meter, we need a force of 1000 newtons. For letter B, work done is equal to the change in elastic potential energy of the spring, that is 1/2 of the spring constant K, multiplied by the square of the final position of the spring, x sub F squared, minus the square of the initial position, x sub I squared. Substituting the values. The spring constant is 1000 newtons per meter, final length is 0.05 meter and the initial position is 0, since the spring starts from its equilibrium position. So the work done in stretching the spring to 0.05 meter from its initial state is 1.25 joules.